If we consider a race, let's say there's 8 runners in the race, and that whoever finishes first will get a gold medal, second, silver, and third, bronze. Then what we want to ask here is how many different outcomes could there be if I'm only interested in the allocation, the winning of the 3 medals. Well, if I start at the top, there's 8 runners who could win gold. Now, once I've allocated the gold, there's 7 remaining runners who could win silver. So once I've fixed the gold and the silver, there are 6 remaining runners who could win bronze. Once I have fixed those 3, I don't care about where the other 5 runners finished in this problem. When we enumerate this, the 8 choices for gold, then 7 for silver, 7 remaining for silver, then 6 remaining for bronze, gives 336 potential outcomes for assigning the 3 medals in any given order: gold, silver, bronze. Now, we wouldn't think of it this way. It would seem like overcomplicating it, but this is because there's 336 possible one-to-one functions mapping the set of 3 medals, gold, silver, bronze, to the set of 8 runners. So we've got 336 possible one-to-one functions, f, which map a set A to a set B, where the set A is gold, silver, and bronze, and the set B is runner 1, runner 2, and so on, up to runner 8. Now, we'll often see this written in factorial notation, this sort of descending order, descending integers multiplied, but truncated at some point. So 8 times 7 times 6, I can think of as 8 factorial, which is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, divided by 5 factorial, so 5 times 4 times 3 times 2 times 1. So by adding in the extra terms at the top and putting them on the bottom, that's a way of writing this sort of truncated product, 8 times 7 times 6, and stopping there, in terms of factorial functions. Now let's generalize this problem, not so we have to have 8 runners and an allocation of 3 medals. But let's say we've got a set of labels A. In the runner example, this would be gold, silver, bronze, and a set of elements of a set B, which would be the runner's identities here. So we'll assume that the cardinality of the set A is less than or equal to the cardinality of the set B. So the way I can assign the first element I wish to allocate, there are the cardinality of B ways of doing that. I can pick any element from B. Once I've done that, there's the cardinality of B minus 1 elements left to pick to assign the second thing to. Then the cardinality of B minus 2 to assign the third thing to. And I go down multiplying these until all of the elements from A are allocated to something from B. And so that's the number of one-to-one functions mapping the set A to the set B. So just as we have the 8 factorial divided by 5 factorial for the runner's example, in general, I've got the number of elements of B factorial divided by the difference between the number of elements in B and the number of elements in A factorial. Now I started this with the in general for the set A being less than or equal to the size of the set B. Now, of course, if the set A contains more elements than the set B, then I can invoke the pigeonhole principle to say that we have no such function. I can't have, for example, one runner and 3 medals to allocate and give each runner a unique medal. If I've got more runners than medals, that's fine. If I've got more medals than runners, then that's a problem.